Imagine for a moment trying to train the world's smartest student, a truly brilliant mind, with this insatiable hunger for knowledge.
Okay.
But here's the twist, and it's a pretty significant one. The only textbooks available for her to learn from are ones she herself has already written.
Sounds a bit self-defeating, doesn't it?
Right. Well, this isn't just some hypothetical for a super student. It's actually a looming reality for advanced artificial intelligence.
Indeed. It's a fascinating and, frankly, profoundly counterintuitive challenge.
Yeah.
One that really threatens to fundamentally reshape the trajectory of AI as we know it.
Yeah.
Today, we're diving deep into what we're calling the data paradox.
Yeah.
This confounding situation where we are absolutely inundated with digital data, yet AI models are increasingly starving for the right kind of data.
That's right. It feels like such a contradiction, doesn't it? So our mission in this deep dive is really to navigate this incredibly complex landscape. We're going to unpack why high-quality human-generated data is becoming so scarce, how this leads to something genuinely concerning known as model collapse, or perhaps more accurately, as we'll discuss, diversity collapse.
Yeah, that's a key distinction.
And then we'll explore whether the emerging solution of synthetic data is this, groundbreaking cure everyone hopes for, or if it's actually a dangerous new problem in disguise.
Right.
What's truly fascinating here, I think, is that this isn't just some technical problem for engineers to solve in a lab.
No, not at all.
It's a profound challenge that touches on truth, privacy, and even the very future of human knowledge itself.
Absolutely. So let's unpack this. Our journey begins with Act 1, the data paradox. And to truly grasp this paradox, we have to start with what we might call the algorithmic appetite, AI's fundamental reliance on data.
Okay.
When we talk about generative AI, whether it's a large language model like GPT-4 or an image generator like Midjourney, it's crucial to understand that these systems don't possess innate knowledge, not the way a human does.
Right. They don't understand quantum physics or, the subtleties of human emotion.
Exactly. Instead, these systems learn by identifying and replicating incredibly intricate patterns, grammatical structures, semantic relationships, all from immense volumes of data.
So think of it this way, maybe. The data isn't just fuel that powers some pre-existing engine.
No.
Instead, it constitutes the entire universe from which the model constructs its operational reality. Its generated content is fundamentally like a rearrangement or combination of things it's already seen.
Right.
It's strictly limited by what it was trained on.
Yeah, it's like a chef who only knows how to cook with the ingredients already in their pantry. They can make amazing combinations, but they can't invent something truly new outside of those ingredients.
That's a great analogy.
So when an LLM is trained, it's often given what seems like a deceptively simple task. Predict the next word in a sequence.
Seems simple enough.
But it does this across hundreds of billions, maybe even trillions of words. This process, known as self-supervision, basically means the model is learning from the inherent structure of the text itself. It doesn't need a human to explicitly label every single piece of information.
Oh, yeah.
It then adjusts billions or maybe even trillions of internal settings, what we call parameters.
Right, parameters. We hear that term a lot.
Through a mathematical procedure, typically backpropagation. Each parameter acts like a tiny switch, sort of influencing the connections between the model's virtual neurons, tuning them to make the best possible predictions based on the patterns it observes in the data.
And this mechanism, it reveals something fundamental, doesn't it? An AI's worldview isn't some deep conceptual understanding of reality.
Not at all.
It's a high-fidelity statistical representation of its training data.
Exactly.
Yeah.
Which is why an LLM can generate a perfectly coherent essay on quantum physics.
But lacks any actual physical intuition.
Right. Or common sense understanding of the world. Its knowledge is purely a reflection of the text it consumed, not an understanding of the underlying physics or reality.
And this dependency, this is the source of both AI's incredible capabilities and its profound vulnerabilities, right?
Precisely. The crucial insight here is that flaws in the data, whether they're biases, errors, or just a lack of diversity, these aren't minor glitches you can just patch over.
No.
They're fundamental distortions of the AI's learned reality. They lead directly to systemic problems, bias, unreliability, and as we'll get into, the very real risk of model collapse.
Okay, that makes sense. It takes us right to the heart of this GIGO principle at scale. GIGO, garbage in, garbage out, how data quality, quantity, and diversity shape AI capabilities.
Yeah, we all know that old computing adage, garbage in, garbage out. But with AI, especially these massive, large-scale models, that principle applies with, well, Amplified force, we're talking about inputs measured in petabytes.
Petabytes, that's 1,000 terabytes. Just trying to grasp the scale.
Yeah. It's mind-boggling. And when you're dealing with that much information, the quality of the output is absolutely inextricably tied to the integrity of the input data. In fact, some estimates suggest that as many as, 85% of AI initiatives are at risk of failure precisely because of deficiencies in their data.
Wow, 85%. That's a staggering figure, isn't it? So let's break down these core pillars of data effectiveness that dictate an AI's capability. Let's start with quality. What exactly makes data high quality in this AI context?
Well, high-quality data is fundamentally accurate. It's clean, it's well-labeled if labels are needed, and it's free of errors, noise, or irrelevant information. This is the most critical factor for building reliable AI systems, period.
Okay.
If you train a model on noisy, biased, or just plain wrong data, its outputs will inevitably be flawed and untrustworthy. Think about trying to learn a language from a textbook just riddled with typos and grammatical errors.
You'd learn all those errors.
You'd internalize those errors. The process of ensuring this quality is rigorous. It involves extensive pre-processing steps like handling outliers, normalizing data formats, ensuring consistency, especially if humans are involved in labeling.
Right.
Without this foundational quality, even a massive amount of data can actually be detrimental rather than helpful. It could just dilute the learning process, introduce noise.
Okay, so quality is king. But what about quantity? We always hear about AI needing massive data sets.
Quantity is definitely essential. Large-scale data sets allow models to learn generalizable patterns and, importantly, avoid something called overfitting.
Ah, yes, overfitting, where it memorizes the training data too well.
Exactly. It learns the training data, including its noise and random quirks, so perfectly that it fails when it sees new, unseen data in the real world. Quantity helps the model see enough variations to generalize better. But, and this is crucial, quantity absolutely cannot compensate for a lack of quality.
You need both.
You need both. Piling on more low-quality data won't fix underlying problems. It might even make them worse.
And then the third pillar, diversity. This seems increasingly important in discussions about AI fairness.
Vitally important. A training data set must be truly diverse and representative of the real-world complexity the AI is expected to navigate. If there's a lack of diversity, say, certain demographics or languages are underrepresented, or rare but critical scenarios are missing, the resulting model will perform poorly across the board. Or worse, it'll generate biased or very narrow outputs.
Right.
A well-diversified data set is crucial for fairness, for inclusivity, and also for ensuring the model can handle the long tail. Those rare events and edge cases it will inevitably encounter out in the wild.
But like a medical AI trained only on data from one ethnic group, potentially misdiagnosing conditions in others.
Precisely that kind of thing. Or an autonomous vehicle needing data on rare road hazards, not just everyday traffic.
And this immense scale of modern AI, these petabytes of data, it creates this amplification effect for any flaws, doesn't it?
Absolutely. Think about it. A minor, seemingly insignificant imperfection in a petabyte-scale data set. Maybe a slight underrepresentation of a particular group in medical images, or a subtle bias in how language describes certain people. That isn't just reflected in the model's output.
It gets magnified.
It gets magnified. The model, in its relentless quest to optimize predictions based on statistical patterns, learns this underrepresentation or linguistic bias as a strong, valid signal. Not an error, but a pattern to replicate.
Oh, wow.
This leads directly to systemically biased outputs, where the model consistently makes unfair or inaccurate predictions for that group. This causal chain is absolutely critical to understanding the challenges of AI ethics and safety.
Yeah.
The sheer scale of modern AI transforms minor data imperfections into potentially major systemic failures.
That's a really powerful point. So to fuel this massive algorithmic appetite, AI draws from all sorts of data modalities, right? It's not just text.
That's right. It's a whole menu. We're talking text data, obviously, the foundation for LLMs, books, news, social media, legal docs, code, you name it.
Then image and video data.
Crucial for computer vision, object recognition, powering those text-to-image generators everyone's playing with.
Audio data.
For speech recognition, voice assistants, transcription services, music generation even.
Code data, too, you mentioned.
Yeah, specialized text from places like GitHub used to train models that can generate, debug, and explain programming code, which is becoming huge.
And finally, maybe less glamorous, but still important, structured and tabular data.
Exactly. Things like financial records, sensor readings, sales data, the kind of stuff used for predictive analytics in businesses.
Okay. And traditionally, how did AI labs get their hands on these colossal data sets? What were the main strategies?
Primarily three main ways. First, and arguably the absolute bedrock of the LLM revolution, was publicly available data.
Right, scraping the web.
Pretty much. AI developers became masters of web crawling, scraping massive amounts of information from the public internet, using datasets like Common Crawl, pulling heavily from public platforms, Wikipedia, Reddit, Stack Overflow, public code repositories.
Okay, that makes sense. What else?
Second, there's proprietary and internal data. Many organizations simply leverage their own data, customer interaction logs, sales records, user behavior data.
Like Spotify using my listening history to recommend songs with its AI DJ?
Exactly that. Or Facebook training its content moderation models on, well, Facebook content. This data is often highly valuable because it's specific and often unique.
And the third way?
Licensed data. As the value of high-quality, curated data became increasingly obvious, a market emerged. AI companies started purchasing datasets from third-party vendors or striking direct licensing deals with content owners.
Like news publishers or book archives?
Precisely. If you want your AI to understand news deeply, you might license data directly from major news organizations.
But here's where it gets, as you said, really interesting, maybe a little foreboding. This heavy reliance on web scraping and public data. You called it the original sin of the current AI paradigm.
I think it can be seen that way, yeah. The crucial insight here is that AI's initial, explosive growth was inadvertently built on a ticking data time bomb. It was a fundamental miscalculation about the infinite availability and, frankly, the zero cost of high-quality, human-generated content online.
So we built this amazing engine assuming infinite free fuel.
Essentially, yes. This strategy created a critical dependency on a resource, the open, human-generated internet that was just assumed to be boundless and freely available for the taking.
And now that assumption is broken down.
Exactly. This dependency has become a single point of failure for the entire field. Because what's happening now, the internet is becoming increasingly polluted with AI-generated content itself, which, as we'll discuss, directly leads to model collapse.
Right, the snake eating its own tail.
And at the same time, more content owners are putting up paywalls, using technical measures like robots.txt or legal threats to block web crawlers.
So the well is getting poisoned and fenced off.
That's a good way to put it. This foundational data source is becoming simultaneously contaminated and inaccessible. And this wasn't some unforeseen accident. It was an inevitable consequence of that initial data acquisition strategy. It directly foreshadows this data crisis we're in. It's a structural vulnerability that was there from the start.
Wow. Okay, that leads us neatly into understanding the exponential ascent, charting the growth of model complexity and data demand. Because it feels like everything just got bigger faster, right?
Explosively so. The last decade has seen this multidimensional expansion in AI development.
Yeah.
The growth in model size, the computational power needed for training, and the sheer volume of data consumed. They're all tightly interconnected. It's like a triad of scale, each driving the others upwards.
It's breathtaking, really. Let's look at model size first, measured by those parameters you mentioned.
Right. Early neural networks, maybe thousands of parameters. Then you jump to GPT-3 in 2020, 175 billion parameters.
Which seemed insane at the time.
It did. And now its successor, GPT-4, is estimated to have somewhere around 1.8 trillion parameters.
Yeah.
Often using a more complex architecture called a mixture of experts.
Mixture of experts, like having lots of smaller, specialized AI brains working together.
That's a good way to think about it, yeah. Different experts handle different parts of a task, but the overall parameter count is enormous. And the trend. Since around 2010, the number of parameters in state-of-the-art AI models has been roughly doubling every single year.
Doubling every year.
Okay.
And the computational power, the compute needed to train these monsters.
That's grown even more dramatically. We measure it in floating point operations per second, or FLOPs. Now, from roughly 1950 to 2010, compute power available roughly doubled every 2 years. That was Moore's law, more or less.
Okay.
But since the deep learning era really kicked off around 2010, this growth has accelerated massively. It's been doubling approximately every 6 months.
6 months? That blows Moore's law out of the water.
Completely. Training a single top-tier model now can consume tens of billions of petaflops. The cost, anywhere from a few $1,000,000 to reports of over $40 million just for the compute time for one training run.
$40 million just for compute. Wow. And of course, to feed these bigger models and use all that compute, the data volume has to keep pace.
It has to. The size of data sets used for training language models has also been doubling roughly every 6 months. Early models trained on millions of words. GPT-3, hundreds of billions of words.
And GPT-4.
The estimates are around 13 trillion tokens.
So
A token is roughly a word or a part of a word, sourced from a mix of public web data and, increasingly, those licensed third-party deals we talked about.
13 trillion tokens. It's almost impossible to comprehend, and this insatiable appetite, this is what's leading researchers to predict we're running out.
Exactly. That's where those projections come from. High-quality language data on the open web, potentially exhausted by as early as 2026.
Okay.
And even the lower-quality stuff may be gone by 2030 or 2050 at the outside.
Okay, the scale is just immense.
And the economic implications of this tight coupling parameters, compute, data, they're profound. It means that to compete at the absolute frontier of AI development, an organization needs massive capital investment across all three pillars.
You need deep pockets.
Very deep pockets.
Yeah.
You need funding for data acquisition, expensive licensing, huge processing infrastructure. You need compute resources, these giant GPU clusters that cost hundreds of millions of dollars. And you need the specialized talent, the PhDs, who can design, build, and train these trillion-parameter models.
Which creates a huge barrier to entry.
Almost insurmountable for most. It concentrates the power to develop these foundational models in the hands of just a few very well-funded technology giants. And that fundamentally shapes the competitive landscape of the entire AI industry.
Which brings us, quite naturally, to Act 2, Model and Diversity Collapse. We've laid the groundwork, we understand the scale and the dependency. Now we face the great contradiction, defining the data paradox.
Right. Despite living in this era of unprecedented digital data creation, data is everywhere. The AI industry is confronting this critical and really counterintuitive challenge, a growing scarcity of the high-quality, usable data required to train the next generation of models.
It's truly confounding, isn't it? We're drowning in data, yet facing a drought of the right kind of data.
Exactly. The specific, high-quality, often compliant data necessary for advanced AI. In this environment, sheer volume can actually become a liability. Without the right tools, governance, quality controls, more data often just means more noise. It makes it harder to find the signal.
So this paradox isn't just one single problem.
No, it's a confluence of powerful trends, all collectively constricting the supply of viable AI training data.
You mentioned this drought of the right kind of data. It still sounds almost contradictory given how much data we generate every day. What's actually causing this scarcity? Is it simply volume running out, or is it more complex?
Oh, it's definitely more complex than just volume. I'd say there are four primary drivers working together here. First, data quality and accessibility.
Okay. The vast majority of data out there, especially in enterprises, but also public data, is unstructured. It's siloed across different systems, it's inconsistent in format, it's often riddled with errors or duplicates.
It's messy.
It's incredibly messy. And this messy data is essentially unusable for AI training without extensive and very costly pre-processing. Think of a big global company trying to unify customer data from dozens of legacy databases, each with different formats, missing fields, making that AI ready. It's a huge, expensive undertaking.
How expensive are we talking?
Well, data preparation alone can consume anywhere from 25% to maybe 35% of an entire AI project's budget. That's a massive chunk just to get the data usable.
Wow. Okay, so quality and accessibility is one driver. What's second?
Second is the sheer cost of acquisition and labeling. Even if you can find potentially useful data, sourcing it, collecting it, cleaning it, and then annotating it, especially if you need human labels, is a major financial and logistical bottleneck.
Labeling medical images or transcribing legal calls must be incredibly time-consuming and expensive. Exactly. And that high cost creates significant barriers to entry, especially for smaller firms or researchers. It limits the scale of projects even for the big players.
Makes sense? Third driver.
Third, regulatory and privacy constraints. This is a big one. Strict data privacy regulations like the EU's GDPR or California's CCPA impose really rigorous requirements. Consent, data minimization, purpose limitation.
All that legal stuff.
Right. And these laws severely restrict the collection and use of personally identifiable information, PII. This makes large-scale web scraping legally hazardous, if not impossible in some cases. And it limits access to valuable real-world data sets, especially in sensitive areas like healthcare or finance, where privacy is absolutely paramount.
Okay, and the fourth driver. You touched on this before.
Yes, the fourth is the depletion of public data. As we discussed, that finite stock of high-quality human-generated data on the public internet is being rapidly consumed by these voracious, ever-larger AI models.
And content owners are locking it down.
Exactly. They're restricting access with technical blocks, paywalls, legal actions, so that, well, a freely available, relatively pristine human-generated content, it's rapidly drying up.
So these four drivers, quality issues, cost, regulations, and depletion, they're all hitting at once.
And they don't operate in isolation. That's the key. They're interconnected, forming this vicious, self-reinforcing cycle.
How so?
Well, the depletion of easy public data forces AI companies into those expensive licensing deals, right? Which dramatically increases costs. At the same time, tightening privacy rules make the remaining public data harder and legally riskier to access. That shrinks the supply even further and drives up the value and the cost of licensed compliant data.
Okay, I see the cycle.
And this high-cost, high-risk environment creates a powerful incentive to turn to synthetic data as an alternative. But, and here's the feedback loop, the improper use of synthetic data can lead to model collapse.
Which pollutes the internet with low-quality AI content.
Exactly.
Yeah.
Which further degrades the value and reliability of the remaining public data commons, making the original scarcity problem even worse.
Wow. It's a nasty feedback loop.
It really is. It isn't just simple resource depletion. It's a complex, systemic challenge with compounding effects. And it seriously threatens the long-term sustainability of the way we're currently developing AI.
This leads us directly to the core of the problem then, model collapse, the Ouroboros of generative AI. As that well of high-quality human data runs dry, developers are increasingly using synthetic AI-generated data to train the next generation of models.
It seems like a logical step, right? If you can't find enough data, make it.
But this practice introduces this profound, and you said insidious risk, model collapse. Explain that. It sounds dramatic.
It is, potentially. Model collapse is basically a degenerative process where an AI model's performance and reliability degrade over successive generations because it's being recursively trained on data produced by its predecessors.
Recursively trained. Trained on its own output or the output of similar models.
Exactly. It's aptly described as an Ouroboros, that ancient symbol of a serpent eating its own tail. Or, maybe less poetically, like an organism continuously breathing in one's exhale. The vital oxygen of real-world information eventually gets depleted.
That's a powerful analogy, breathing in your own exhale. So how does this degradation actually happen mechanically?
Think of it like making a photocopy of a photocopy over and over again.
Okay, I can picture that. Each copy gets a little worse.
Precisely. With each iteration, the small errors, the statistical artifacts, the inherent biases of the parent model, they aren't corrected. Instead, they are captured and actually amplified by the child model.
Amplified, okay.
And a crucial aspect of this process is the loss of diversity. Generative models, by their very nature, tend to learn and reproduce the most common patterns in their training data. That's how they work.
Right, they find the average, the typical.
Exactly. So over multiple generations of this self-feeding, they start to oversample these common high-probability events. And they undersample and eventually just forget the rare but critically important data points out in the tails of the distribution.
They forget the outliers, the weird stuff.
The weird stuff, the niche stuff, the exceptions. The model's learned perception of reality starts to drift away from the true distribution. It becomes a caricature, a smoothed out version, until entire concepts might get blurred or just erased from its memory.
That's quite a detour. You know, it reminds me of that game Telephone we used to play as kids. You whisper a message down the line.
Oh, yeah.
By the end, the original message was utterly unrecognizable. It sounds like AI is playing a global game of telephone with itself. But if it's like making copies of copies, are these models doomed to eventually just drift into utter gibberish? Or is there a way to, prevent this Ouroboros from devouring itself completely?
That's a great question, and it's really where the nuance comes in. Because the consequences of model collapse, if it happens unchecked, are pretty far-reaching and severe.
Like what?
Well, first, you just get degraded and unreliable outputs. That's the most immediate effect. The quality of the AI's generated content declines. Text becomes increasingly repetitive, maybe nonsensical, detached from reality.
You mentioned an experiment with jackrabbits.
Yeah, there were some lab studies where an LLM fine-tuned over several generations purely on its own output, when prompted about, say, architecture, eventually just started outputting incoherent text about jackrabbits.
Oh, okay.
Image models similarly start producing less diverse and lower quality visuals. One study showed a model trained initially on diverse faces began generating much more homogeneous, similar-looking faces after iterative training on synthetic data.
So less variety, less quality, what else?
Then there's knowledge decline and amplified bias. As models forget that long-tail data, the rare events, the niche topics, the minority perspectives, they literally lose knowledge.
That seems bad.
It is. It not only limits the scope of knowledge accessible through AI, but also exacerbates existing societal biases. The model's worldview narrows to reflect only the most common mainstream patterns. It forgets the richness and diversity of the real world.
So if you ask an AI for creative ideas, it might just give you increasingly bland, similar stuff.
Exactly. It might consistently produce similar plots or characters and stories because its exposure to diverse human creativity has diminished through this recursive loop. It loses the ability to be truly novel.
And for businesses relying on AI for actual decisions.
That leads to poor decision-making. If an AI medical diagnostic tool forgets how to identify a rare disease because those cases were underrepresented and eventually dropped out of its synthetic training diet, that's dangerous.
Or a financial risk model missing a black swan event.
Precisely. If these low-probability, high-impact scenarios get filtered out over generations of training, the model becomes useless, or worse, misleading when you need it most.
And the big picture, societally.
The ultimate risk is the erosion of information integrity. Widespread model collapse, even a partial one, threatens to pollute the entire digital ecosystem with vast quantities of low-quality, biased, and just inaccurate information. It could potentially turn the internet into that unusable information junkyard people worry about.
Making it impossible to tell what's real or true online.
Yeah, fueling misinformation, making it incredibly difficult to discern truth from fiction.
Okay, so that sounds pretty bad. But you mentioned nuance regarding my gibberish question earlier. Is it always this catastrophic decline?
Right, it's crucial to offer that nuance. The most alarming predictions of model collapse, the ones where models descend into producing complete, incoherent garbage, like the jackrabbit example, often stem from these early laboratory simulations. These simulations typically use an unrealistic replace paradigm.
Replaced paradigm, meaning?
Meaning they assumed that in each generation, the old data was entirely replaced by new synthetic data, just AI feeding on AI.
Which probably isn't how it works in the real world.
Probably not. More recent and critical research, including findings published in journals like Nature around 2025, and studies from places like Apple's Language Models Research Team, argues that real-world AI development tends to follow more of an accumulate paradigm.
Accumulate paradigm.
Where synthetic data is added to the existing pool of real data and maybe prior generation synthetic data. It's mixed in, not a full replacement.
Okay, so under that more realistic scenario.
A complete catastrophic collapse into total gibberish is less likely. The presence of some real data acts as an anchor, to some extent.
Phew. Okay, so maybe not total gibberish, but does that mean we're out of the woods?
Not necessarily. This doesn't eliminate the danger. Instead, it points to a more subtle, but maybe equally pernicious phenomenon. What we're calling diversity collapse.
Diversity collapse. Okay, explain that.
Even when synthetic data is mixed with real data, if you keep recursively adding AI-generated content that tends towards the average, the model gradually loses its understanding of the data distribution's tails, the outliers, the nuances.
So it still produces coherent output. It sounds okay.
Yeah, it might still produce grammatically correct, seemingly coherent text or images, but they become increasingly generic, biased towards the mean, less capable of handling nuance, creativity, or novel situations.
So it's not gibberish, it's just bland mediocrity.
Kind of, yeah. That Apple LRM study from 2025, for instance, showed exactly this. The models retained grammatical coherence. They could still talk, but their accuracy on complex multi-step reasoning puzzles, it would free fall over successive generations of mixed synthetic training.
Why?
Because the nuanced, long-tail relationships and knowledge needed for that deep reasoning were gradually being forgotten, smoothed over by the synthetic data's tendency toward the average.
Okay, that makes sense. The subtle connections get lost.
Exactly. So the most practical takeaway, maybe the thing you should really worry about day to day, isn't that AI will suddenly start speaking nonsense. It's this creeping digital blandness. A world where models amplify the common denominator and lose the rich nuance that makes human knowledge, creativity, and problem-solving truly valuable.
Like a customer service bot that can only handle the most common questions and gets totally lost with anything unusual.
Perfect example.
Yeah.
Or a creative writing assistant that only produces formulaic, predictable plots. This shift in focus from a dramatic sci-fi model collapse to a more gradual, real-world diversity collapse is essential for actually diagnosing the problem and finding effective ways to fight it.
Right. Which brings us neatly to Act 3, the rise of synthetic data. Because in response to this whole escalating data crisis, The scarcity, the cost, the looming threat of collapse the AI industry has really championed synthetic data as its leading technological solution.
It makes sense on the surface, doesn't it? If you can't get enough good, real data, maybe you can just make perfect data yourself.
The idea is to artificially generate data that mimics real-world information, promising to overcome all those challenges we talked about: scarcity, privacy concerns, even bias.
But the big question is it truly a panacea?
Yeah.
A cure-all? Or is it more like opening Pandora's box, introducing a whole new set of problems?
Let's define it first. What is synthetic data exactly?
At its core, synthetic data is artificially generated information. It's created algorithmically, not collected from real-world events. The key goal is that it mimics the structure, the patterns, the statistical properties of a real data set it's based on.
And the crucial part for privacy.
Crucially, it contains no one-to-one mapping to real individuals or real events. This is what allows it, in theory, to be used for analysis, model training, testing, whatever, without exposing sensitive or personally identifiable information, that PII.
Okay, so it looks like real data statistically, but isn't actually real people's data. Does it come in different flavors?
It does. This technology exists on a spectrum, really, offering different trade-offs between how realistic the data is, its fidelity, and how much privacy it provides. We can kind of define a taxonomy.
Okay, let's hear it.
First, you have fully synthetic data. This type is entirely artificial, is generated completely from scratch by a model that has learned the statistical distribution of some real data set.
So no real data points are included at all.
None. Because of that, it offers the highest level of privacy protection. Re-identifying individuals is, nearly impossible. An example might be generating a completely new set of patient record symptoms, diagnoses that are statistically similar to real patient data, but refer to no actual person.
What's the downside?
The potential cost is lower fidelity. Because it's purely generated, it's only an approximation of the real world. It might miss some subtle correlations or complexities.
Okay, fully synthetic. What's next?
Second, there's partially synthetic data. This is more of a hybrid approach. Here, you take a real data set, but you only replace specific sensitive attributes or columns with synthetic values.
Like names, addresses, social security numbers.
Exactly. Things that directly identify someone. The rest of the data, maybe purchase history, demographic info, remains real.
So you keep more of the original structure.
Right. It tries to strike a balance, preserving much of the original data structure and relationships, while protecting the most obviously sensitive bits. It is, however, more complex to implement correctly. And there's always a risk that sensitive patterns could still be inferred if you're not careful about how you do the replacement.
Okay, and the third type?
Third, there's something called hybrid synthetic data. This technique involves creating a fully synthetic data set, like the first type, but then you actually mix its records with randomly selected records from the original real data set.
So you're blending real and fake records together. Why?
It further obfuscates potential re-identification. It makes it even harder for someone looking at the dataset to figure out which records are real and which are fake, or to link patterns back to specific real individuals or sensors. It offers a pretty robust balance of utility and privacy. Imagine using it for smart city data, mixing real sensor readings with synthetic ones.
Interesting. So different approaches for different needs. How is this stuff actually generated? What are the tools?
It relies on a really diverse toolkit of generative models. Different methods are suited for different data types and objectives. Think of them as specialized artists, each with their own strengths and weaknesses.
Okay, give me some examples.
Well, you have relatively simple statistical methods. These are fast, good for well-understood data distributions, but limited in capturing really complex relationships.
Then the more advanced stuff, like GANs.
Exactly. Generative adversarial networks, or GANs. These use that clever setup with a generator creating data and a discriminator trying to tell if it's real or fake. They compete, and the generator gets really good at making realistic outputs, especially good for images, maybe even video or deepfakes.
But they have downsides.
Yeah, they can be notoriously unstable to train and sometimes suffer from mode collapse, where they only generate a limited variety of outputs.
Okay, what else is in the toolkit?
There are variational autoencoders, or VAEs. These are generally more stable to train than GANs and good at learning the underlying structure of data. Often used for image generation or finding anomalies. Their outputs can sometimes be a bit blurrier or less sharp than the best GANs, though.
And the newer techniques. I hear a lot about diffusion models.
Diffusion models have really taken the lead recently, especially for image and video synthesis. They work by starting with random noise and iteratively refining it into a coherent sample. They produce exceptionally high quality and diverse results, often state-of-the-art.
The catch.
They are very computationally intensive to train and run.
Right. And for text or sequential data?
For that, you often use transformer models, the same kind of architecture underlying models like GPT. Their self-attention mechanism is brilliant at learning the patterns and structure of language, code, or even structured tabular data. You can use them to generate synthetic versions of all that.
But they need a lot of pre-training data themselves, right?
They do. So understanding this toolkit is crucial. The strategic choice of which generative method to use dictates the quality, the cost, the privacy trade-offs, and ultimately the suitability of the synthetic data for its intended purpose. You wouldn't use a simple statistical method for a complex computer vision task, nor a costly diffusion model for basic tables.
It requires a sophisticated data strategy just to make the synthetic data, let alone use it.
Exactly. It's not a magic button.
So let's talk about the promise of synthesis. Why is everyone so excited? Addressing scarcity, privacy, bias. What are the big selling points?
Well, the most immediate and obvious benefit is overcoming that data scarcity and cost problem we discussed.
Right, just make more data.
Pretty much. It's the ability to generate vast quantities of potentially labeled data on demand. This provides a scalable and hopefully cost-effective alternative to traditional, often painful, data collection.
Which is huge for smaller players.
Absolutely. It's particularly valuable for smaller organizations, startups, researchers who lack the resources for massive data acquisition campaigns. Or even for large companies working on problems where historical data is just limited or non-existent. By automating data creation, it can significantly reduce project timelines and costs.
Okay, addressing scarcity. What about privacy?
That's another huge draw. By creating statistically realistic data that, ideally, contains no real comfort. Personally identifiable information, synthetic data allows organizations to innovate without violating strict privacy regulations like GDPR or IPR.
So you can train models or test software without using real customer data.
Exactly. It enables secure data sharing for collaboration, maybe releasing public data sets for research, developing and testing software in highly regulated industries like finance or healthcare. It effectively de-risks parts of the development process from a privacy standpoint.
And the third big promise, mitigating bias. This sounds almost too good to be true. How can fake data fix real bias?
Well, this is a really powerful idea, potentially a game changer. We know real-world data sets often reflect historical biases or underrepresent certain groups or rare events. Synthetic data generation offers the potential to intentionally engineer corrections for these imbalances. Developers can choose to oversample underrepresented populations in the synthetic dataset. They can create perfectly balanced datasets for fairness testing, or they can specifically generate examples of critical edge cases that a model might rarely encounter in the wild.
So you could say, create more examples of loan applications from an underrepresented group to train a fairer financial model.
That's the idea. By doing this, you can directly aim to improve model fairness, robustness against rare events, and overall performance. It's a proactive way to try and shape the data towards a desired outcome, rather than just passively accepting the biases in historical data.
Okay, those are compelling benefits. Are we seeing this used in the real world already?
Yeah.
In high-stakes areas?
Definitely. Adoption is growing rapidly, especially where real data is just too sensitive, too scarce, or too dangerous to collect at the scale needed. Healthcare is a prime example.
How so?
Synthetic data is being used to train diagnostic AI models, maybe on rare diseases, without compromising patient confidentiality. Researchers can simulate clinical trials with synthetic patient cohorts, potentially accelerating drug discovery. And it allows for secure sharing of rich, realistic patient-like data for collaborative research that would be impossible with real PII.
What about finance?
Similar story. Institutions are using synthetic data to train fraud detection models. It's hard to get enough real examples of novel fraud tactics, right? So they generate realistic synthetic examples.
Create fake fraud to catch real fraud.
Kind of.
Oh.
It's also used heavily to stress test risk assessment models, simulating those black swan market crashes or other extreme scenarios that rarely happen in real data, but you need your models to handle.
Yeah.
And developing personalized financial services without exposing sensitive customer account details.
And you mentioned autonomous vehicles earlier. That seems like a perfect use case.
It's practically indispensable there. It's simply impossible or incredibly dangerous and expensive to collect real-world driving data for every conceivable scenario an AV might face.
Like a specific type of crash in a blizzard at night.
Exactly. Simulation platforms, powered by generative models, can create limitless permutations of traffic conditions, adverse weather, pedestrians doing unexpected things, critical edge cases, all the stuff that's rare but deadly.
So they can train and test the AI in simulations safely?
And scalably. It allows developers to train and validate the perception and decision-making models in a safe, controlled environment. It's absolutely crucial for ensuring the safety and reliability of self-driving systems before they hit public roads.
It sounds like, especially for things like AVs or rare events, the real power isn't just replacing real data, but creating data that's impossible to get otherwise.
That's a really important distinction. While many initially viewed synthetic data as just a replacement for scarce real data, its most powerful function is arguably in augmentation and simulation. The unique value isn't just quantitative providing more data, it's qualitative providing entirely new, otherwise unobtainable data.
Like that specific accident scenario for AVs.
Or for finance, simulating the market impact of a once-in-a-century geopolitical crisis. This capability enables a level of model testing, validation, and robustness that real data alone can simply never provide. It pushes the boundaries of what's possible in AI development by letting us explore scenarios beyond our limited real-world experience.
Okay, the promise is clear. But as with any powerful new tool, there have to be downsides, right? Which brings us to the perils of synthesis, a critical examination of limitations and risks.
Absolutely. Despite its significant promise, synthetic data is definitely fraught with limitations and potential risks that demand really critical examination. Just jumping onto the synthetic data bandwagon without understanding these downsides can lead to flawed models, create new ethical dilemmas, and ultimately undermine the very goals you're trying to achieve.
So what's the first major concern?
One big one is the fundamental lack of realism and nuance. Synthetic data is, by definition, an approximation of reality. It's a model of the data, not the data itself.
Even the best generative models can't capture everything.
Exactly. They can struggle to capture the full complexity, the subtle correlations, the unexpected outliers, and just the inherent messiness of real-world data. Outliers and those low-probability events in the tails are particularly difficult to model accurately while also preserving privacy.
So if you train a model only on perfect synthetic data,
it might perform beautifully in simulations, but then prove brittle and unreliable when deployed in the noisy, unpredictable real world. Imagine a synthetic medical data set that, in trying to be clean and statistically average, smooths over those subtle, messy indicators of a rare disease that an experienced human doctor would recognize. The AI trained on it might miss those crucial signals.
Okay, lack of realism. What else? This seems counterintuitive given the promise of fixing bias.
Right, the introduction of new and amplified biases. While synthetic data can be used to mitigate bias, the generation process itself can inadvertently introduce new biases, or even amplify existing ones from the source data it learned from.
How?
Well, if the original data set used to train the generator was biased, the generative model will learn and likely perpetuate those biases unless it's explicitly and perfectly corrected during the generation process, which is hard.
And auditing that is difficult.
Very. Especially with complex black box models like GANs, it can be really hard to understand exactly how biases are being created or embedded in the synthetic output. And the whole act of correcting bias is itself an ethical minefield.
Who decides what's fair?
Exactly. Who defines fairness? You risk overreaching and creating a distorted, idealized version of reality rather than a truly representative one. If you overcorrect for one perceived bias, you might inadvertently create a new, unexpected one. It's a tricky balancing act.
Okay, bias is still a risk. What other challenges?
Validation and quality assurance challenges are another major hurdle. This is a big practical problem. How can you actually be sure that the artificial data you've generated is a faithful proxy for reality, that it's accurate and representative enough?
You'd need to compare it to real data.
Right, which requires rigorous validation against high-quality real data. But if the whole reason you're using synthetic data is because real data is scarce or unavailable,
you're stuck in a circular problem.
Exactly. It's like trying to check if a photocopy is accurate when you've lost the original document. Without robust validation methods, organizations risk training their models on flawed or misleading artificial data, leading to poor performance or unexpected failures down the line.
And finally, the big one we talked about earlier, the long-term risk of homogenization and collapse.
Yeah, this is the long-term systemic risk. Research into the widespread long-term effects of synthetic data use is still relatively early. But a significant concern is that an over-reliance on it, especially validation is weak, could lead to that feedback loop of homogenization.
Where AI models become less creative, less diverse.
Less connected to the messy, evolving real world. And in the worst-case scenario, this could trigger the very model collapse or diversity collapse phenomenon that synthetic data is sometimes intended to prevent. You end up creating a generation of AI models trained on an increasingly distorted, self-referential, artificial view of reality.
Wow, that really brings the paradox full circle.
It does. And all these challenges really highlight a fundamental, inescapable tension at the very heart of synthetic data. The privacy-utility trade-off.
Explain that trade-off.
Okay. To be useful for training AI models, synthetic data must accurately replicate the statistical properties of the real data it's based on. It needs to capture the patterns, the correlations.
Right, it needs high fidelity.
But the more accurately it replicates these properties, the more information it can potentially leak about the original data. This increases the risk of privacy breaches, like those membership inference attacks, where an attacker tries to figure out if a specific individual's data was part of the original set used to train the generator.
So more useful means potentially less private?
Generally, yes.
Yeah.
Conversely, to make synthetic data truly private, you often need to introduce some degree of distortion, add noise, or smooth things out. But doing so reduces its utility, its fidelity. It makes it less accurate as a representation of reality.
So you can't have perfect utility and perfect privacy simultaneously.
It seems to be a fundamental constraint. A perfectly useful synthetic dataset is probably not perfectly private, and a perfectly private one is probably not perfectly useful for complex tasks. This inherent trade-off means that synthetic data, despite its power, can likely never be a perfect drop-in replacement for real data in all situations.
So it's a powerful tool, but needs careful handling.
Exactly. It's a powerful but imperfect supplement, something that needs to be carefully managed, validated, and likely blended with real data, not seen as a magic substitute.
Okay. This brings us to Act 4, the mid-2025 pulse check. We've dissected the problem, we've explored the promise and perils of synthetic data. But how is all of this actually playing out right now, say, mid-2025, in the real world? Let's take a pulse check on the ethical issues, the economic shifts, and the strategies emerging from this whole data landscape.
Good idea, because theory is one thing, practice is another.
Let's start with the ethical and societal fault lines that are emerging. A future where a significant chunk of the information we consume daily is generated by AI that presents some pretty formidable societal challenges, right?
Absolutely. The proliferation of synthetic content, text, images, video, audio threatens to flood our digital infosphere with material that is increasingly difficult, maybe impossible sometimes, to distinguish from human-generated reality.
Which could really erode trust.
Massively. It could lead to a systemic degradation of trust in online information generally. Imagine a world where the transaction cost of verifying any piece of information becomes prohibitively high for the average person.
That sounds like it could create a new kind of digital divide.
Exactly. A divide where maybe only the affluent or the technically savvy have the resources or skills to reliably discern truth from fiction, while everyone else is left navigating this potential unusable information junkyard.
And that kind of environment is ripe for exploitation.
Hugely. The potential for such an environment to be exploited for targeted misinformation, manipulation, propaganda, it could seriously endanger democratic processes, social cohesion, you name it.
And legally, this also creates headaches, right? Redefining privacy, ownership, and consent.
Oh, big time. Synthetic data introduces really novel and complex ethical and legal gray areas. For instance, if an organization creates a highly accurate synthetic twin of your health data, does your original consent for using your real data automatically apply to this artificial copy?
Good question. What do the laws say?
Well, regulations like GDPR do apply to the processing of personal data, which includes the act of synthesis itself. Creating synthetic data from real personal data is a regulated activity.
Okay.
However, once a fully synthetic data set is created that supposedly can no longer be traced back to individuals, it might fall outside the scope of these current privacy laws. This creates a legal ambiguity that's still being figured out, and it's already sparking things like early GDPR class action threats against companies using these techniques.
So who owns the insights from synthetic data? What rights do the original people have?
These are critical questions without clear answers yet. It raises fundamental issues about ownership, benefit sharing, and the residual rights of the original data subjects whose information, even indirectly, made the synthetic data possible.
And then in those high-stakes areas we talked about, healthcare, criminal justice.
That's where you see the high-stakes ethical dilemmas most clearly. The use of synthetic data there presents really acute ethical challenges. In healthcare, as we said, an AI trained on synthetic data that inadvertently inherits or even creates a bias could lead to life-threatening misdiagnoses for certain groups.
And in policing.
In criminal justice, using synthetic data to train predictive policing models, you run a huge risk of creating or amplifying systemic biases. This could lead to discriminatory outcomes, reinforcing historical inequalities, targeting certain communities unfairly. Ensuring fairness, accountability, and meaningful human oversight in these applications is absolutely paramount. Errors aren't just statistical noise, they have profound human consequences.
And one more ethical dimension we haven't touched on much, the environmental cost of data.
Yes, that's crucial too. This insatiable demand for more data, and especially for more computational power to train these gigantic AI models, carries a significant and growing environmental footprint.
Data centers use a lot of power and water.
Staggering amounts. The data centers powering this generative AI gold rush consume enormous quantities of electricity for computation and vast amounts of fresh water, often for cooling their hardware. Back in 2022, the global electricity consumption of data centers was estimated at around 460 terawatt-hours.
How much is that?
That puts their energy use somewhere between the entire nations of Saudi Arabia and France, just the data centers.
Wow.
And training a single large model like GPT-3, estimates suggested it consumed over 1,287 megawatt-hours of electricity. That's equivalent to the annual energy use of over 100 average U.S. homes, just for one training run of one model.
And models are only getting bigger.
Exactly. As models continue to scale, these environmental pressures, energy consumption, water use, carbon footprint, will only intensify. It raises really critical questions about the long-term sustainability of the current AI development trajectory. Can we afford this path?
It really feels like synthetic data is this double-edged ethical sword, doesn't it?
That's a perfect way to put it. On one hand, it offers compelling potential solutions to pressing ethical problems, protecting privacy, maybe creating fairer data sets.
But on the other hand,
it introduces this whole new, challenging set of ethical risks. The potential for hidden algorithmic bias, the threat to our shared information reality, these novel dilemmas around consent and ownership, the environmental cost. A responsible AI strategy can't just assume synthetic data is inherently more ethical.
you have to actively manage the new risks.
You have to actively navigate this new and complex ethical landscape. You have to recognize that you're often trading one set of well-understood challenges for another, more novel and perhaps more insidious set of problems.
Okay, let's shift to the economic and competitive landscape. This data paradox isn't just technical or ethical, it's a huge economic force reshaping business models and the tech industry, right?
Absolutely. We're even seeing what some analysts are calling a Gen AI paradox emerge.
Gen AI paradox.
Yeah, surveys show that while a huge number of companies, maybe nearly 8 in 10, have deployed generative AI in some form,
They're trying it out.
a similarly high percentage report, no material impact on their actual earnings or productivity yet.
Why the disconnect?
A key reason seems to be that these data accessibility and quality gaps we've been talking about are preventing most of the truly high-value function-specific AI use cases from moving beyond the pilot or experimental stage. They can't get the right data to make it work reliably at scale.
Interesting. And this is creating different tiers of companies.
It seems to be contributing to a kind of two-tier AI economy. On one tier, you have the large established tech giants. They're leveraging their massive proprietary data sets there of human-generated content, mostly collected before 2022 or so, before widespread AI pollution.
That data is like gold now.
Exactly. It acts as a significant competitive moat. They have this huge historical advantage in a world where new, high-quality public data is scarce and increasingly contaminated. Access to this unique, relatively uncontaminated data entrenches their market position.
And the other tier?
Meanwhile, you have more agile startups, often unburdened by legacy systems or data. They're using AI, sometimes synthetic data, sometimes just more clever data-efficient techniques to build entirely new business models from the ground up. They're maybe focusing on niche problems where data needs are smaller.
And this whole situation has fueled the rise of a specific market.
Oh yeah, the synthetic data market itself. An entire industry has sprung up specifically to address the data paradox. and it's experiencing explosive growth.
What kind of numbers are we talking?
Forecasts project its market value to soar from maybe $200, $300 million back in 2023 to potentially between $3.7 billion and $6.5 billion by 2030 or 2032.
Wow, that's huge growth.
It's a compound annual growth rate somewhere in the range of 35% to 46%. It's massive, driven by that rising demand for AML training data, increasing privacy concerns, the need for cost-effective solutions, and just the general advancements in generative AI making synthetic data better.
Who are the key players in this market?
It's a mix. You have the big tech companies, AWS, Microsoft, Google, NVIDIA, all offering synthetic data tools or platforms. And then you have a growing number of specialized startups focusing purely on synthetic data, like Synthesis AI, Griddle.ai, Tonic.ai. Many of these are really embracing a synthetic data-first approach to AI development.
So how is this reshaping the overall competitive landscape? Is it helping the big guys or the startups more?
It's doing both, which is interesting. On one hand, the underlying data paradox reinforces the dominance of the incumbents with their proprietary data moats. Real, high-quality human data is still king if you have it.
But synthetic data offers a way around that.
Exactly. High-quality synthetic data generation also acts as a potentially potent democratizing force. It could level the playing field by lowering the barrier to data access.
Oh.
Startups and smaller firms can now potentially generate the high-quality, diverse, privacy-compliant data they need to train robust models, allowing them to compete with larger players without needing to build those massive, expensive, real-world data collection infrastructures.
So faster innovation, maybe?
Potentially, yes. Faster innovation cycles, more efficient software testing, quicker product development. It could foster a more vibrant and competitive ecosystem overall. The future landscape will really be defined by this struggle, the concentrating force of proprietary real data versus the democratizing potential of synthetic data.
You mentioned a Substack survey showing maybe a shift in thinking.
Yeah, some mid-year surveys, like one highlighted on Nate's newsletter, showed increasing skepticism among some VCs and startups about the viability of building massive general-purpose AI models to compete with the giants. Instead, there's a pivot towards more specialized, often more data-efficient models targeting specific industry problems where synthetic data or smaller real data sets might be sufficient.
Very interesting. So given all this, what are the practical strategies for a sustainable AI ecosystem? How do we navigate this?
Well, addressing this data crisis really requires a multi-pronged approach. It needs immediate technical fixes combined with perhaps a more fundamental shift in development philosophy.
Let's start with countering model and diversity collapse directly. What's being done there? I think you mentioned a synthetic summer trend report.
Yeah, that term popped up, highlighting the focus on these strategies. Several practical approaches are being deployed. A critical component is maintaining a strong human-in-the-loop HITL approach.
Humans checking the AI's work.
Essentially, yes. For verification, quality control, ensuring that AI-generated content or data is vetted against real-world standards and doesn't drift too far into unrealistic territory. Keeping humans involved in the curation and validation process is key.
What else besides HITL?
Probably the most effective strategy against collapse right now is to consciously curate the training data sets. Don't just rely on synthetic data alone. Ensure a healthy mix of authentic, high-quality human-generated data and carefully validated synthetic data. That mix helps prevent the model from drifting too far from ground truth.
Maintaining that anchor to reality.
Precisely. Furthermore, techniques like retrieval augmented generation, or RAG, are becoming very popular.
RAG, how does that help?
RAG essentially grounds the model in real time. Before generating a response, the LLM is allowed to query an external, trusted knowledge base, like a specific database of company documents or verified facts.
So it looks things up before it answers.
Basically, yes. This helps significantly reduce hallucinations making stuff up and tethers its outputs more closely to verified current information. It's another way to combat the drift caused by purely generative processes.
These seem like important tactical fixes. What about bigger strategic shifts? You mentioned moving from model-centric to data-centric AI.
Yes, this is potentially a very significant strategic shift, championed by people like Andrew Ng for a while now. For years, the main focus of AI research was on iterating and improving the model architectures, the algorithms, making bigger, better models.
Okay.
The data-centric paradigm argues that for many real-world applications, the models themselves are now sufficiently advanced. The code is a solved problem, as Ng sometimes puts it.
So the bottleneck isn't the model anymore.
Increasingly, the bottleneck is the data The biggest gains in performance, reliability, and fairness will come from systematically engineering and improving the data itself.
How do you engineer data?
It involves treating data improvement not just as a one-off pre-processing step before training, but as an iterative process throughout the entire AI development lifecycle. It means focusing on creating consistent data labels, using error analysis to find and fix the specific data issues that are most hurting performance, and collaborating really closely with subject matter experts to inject their domain knowledge directly into the data curation and labeling process.
So focusing effort on the quality and structure of the input, not just the algorithm.
Exactly. Smart data over just big data.
And speaking of moving beyond big data, is the paradox forcing exploration of other, less data-hungry ways to build AI?
It absolutely is. The sheer cost and difficulty of acquiring massive, high-quality datasets is pushing the industry to explore alternative development paradigms that are less data-intensive and more efficient.
Like what?
Well, one clear trend is a greater focus on smaller, task-specific models. Instead of trying to build one giant model that does everything, build smaller models that are really good at one particular application.
Yeah.
These usually require much less data to train effectively.
And techniques like transfer learning.
Yes, transfer learning is huge here. You take a massive model that was pre-trained on a giant data set, often by one of the big labs, and then you fine-tune it on a much smaller, specific data set relevant to your particular task. This lets you leverage the power of large models without needing petabytes of your own data.
Are there totally different approaches to getting data too?
People are exploring things like data donor ecosystems, creating frameworks where individuals can explicitly consent to share their anonymized data for specific public good initiatives, like medical research. This could create new, ethically grounded sources of data.
And focusing on smart engineering over just brute force data.
Right. Some approaches emphasize human capital, clever engineering, and open source collaboration over just having the most data and compute. We saw examples like the DeepSeek models achieving surprisingly competitive performance, with reportedly much lower training costs, allegedly through innovative engineering and leveraging open community efforts. It shows that more data isn't always the only answer.
So as we navigate this whole complex evolution, what are the big open questions for the future? What should we be watching?
There are several critical open questions that will really define the research agenda, policy debates, and strategic decisions for the next decade, I think. First, data and AI governance. This is huge. How can we establish robust, ideally global, standards and frameworks for governing both real and synthetic data?
Covering quality, privacy, ethical use, auditing.
All of it.
Yeah.
Ensuring quality, protecting privacy, defining ethical use cases, figuring out how to audit these complex systems for bias or failure. This isn't just about technical standards. It requires international cooperation on what constitutes responsible AI development and deployment. Second, human-AI interface. What is the optimal model for collaboration between humans and these increasingly autonomous AI systems? How do we design effective systems for that human-in-the-loop oversight we talked about? How do we build intuitive feedback mechanisms? How do we best leverage expert knowledge in data curation and model validation? It's about designing a true partnership, not just building a tool.
Third, sustainability.
Third, economic and environmental sustainability. How can the AI industry possibly reconcile this exponential growth in computational demand with finite energy and water resources? Developing more energy-efficient hardware like neuromorphic chips, more efficient algorithms, promoting smaller, specialized models. This isn't just a technical challenge, it's an environmental and economic necessity for the field's long-term health.
Fourth, integrity of information.
Fourth, the future of knowledge and information integrity. In this ecosystem increasingly saturated with AI-generated content, how do we preserve the diversity, the authenticity, and the fundamental integrity of human knowledge? This involves developing better tools for content provenance, like reliable watermarking or metadata standards so we know where information comes from. But it also means fostering a culture of critical information consumption in the public. It's fundamentally about maintaining trust in what we read, see, and hear online.
And finally, the big paradigm shift.
And finally, yes, the paradigm shift itself. Can the industry successfully transition from the big data paradigm that defined the last decade or so to a more efficient, sustainable, and maybe more intelligent, smart data paradigm? The ultimate test, perhaps, will be developing AI that can learn effectively and continuously from sparse, dynamic streams of data like humans do, rather than always requiring these massive static data sets for batch training. That would be a fundamental leap.
Wow. We have covered a lot of ground here. We've truly unpacked this core challenge. AI's insatiable appetite for data hitting the wall of finite, high-quality human knowledge. This leads to the complex risks of model collapse, or maybe more accurately, diversity collapse. And we've seen how synthetic data offers this compelling, yet really double-edged solution. It's clearly a testament to human ingenuity, but it also acts like a mirror, reflecting our existing biases and raising these profound questions about truth, trust, and reality.
Absolutely. And I think the key actionable insight from this deep dive, if there's one thing to take away, is clear. The future of AI isn't just about building bigger, smarter models. It's fundamentally about how we understand, how we value, and critically, how we manage the data that feeds them.
It's all about the data in the end.
It really is. The path forward demands this careful blend of human insight, rigorous curation, responsible governance, and genuinely innovative approaches to both data creation and data management.
So, as we wrap up, here's a final thought for you, our listener, to mull over. As our digital world becomes increasingly populated, maybe even dominated by AI-generated content, it raises a really important question. How will we as humans define and truly value authentic human knowledge, creativity, and unique experiences in this increasingly synthetic future?
Yeah, what will truly differentiate something crafted by human hands and minds with all its flaws and quirks from something perfectly synthesized by an algorithm?
What makes a human touch special? And how do we preserve it? We invite you to think about that question long after our deep dive concludes today.